We'll consider first the operator given by the formal expression in L2 on the half line from 0 to plus infinity, with the potential being the sum of the infinite sum of some indicator functions of the intervals from x k minus 1 to xk with some real coefficients ak, on the natural domain being W22 on the half line, the Sobolev space, with the boundary condition at 0 being Dirichlet boundary condition. We can also consider Neumann condition, but there are non-significant changes to the whole picture. The problem we're going to study is given a closed subset S of R of real line, we will try to find, if it is possible, the values xk and ak such that the essential spectrum of such operator is precisely S. We know that the essential spectrum must be closed, so this condition is not omittable. But is it possible to for the essential spectrum to be the arbitrary closed subset of real line? We will show that it is possible indeed. The main idea of this method is to consider some auxiliary operator L hat being the prime sum. In this case, it is the prime sum of some operators on the intervals from xk minus 1 to xk, which are given as the Sturm-Liouville operators with some constant potential on the finite segment. This operator indeed is the restriction of the original operator on the subdomain, being putting additional Dirichlet conditions on the points xk. The first proposition we are going to show that if lambda is regular for both of these operators, then the resolvents R lambda of L and R lambda of L hat are indeed equal. So in this case, the proof is very straightforward. For f being from L2 on the half line, we will consider the functions u being R lambda of f, which belongs to the domain of operator L, and the function v being R lambda of L hat, being from the domain of L hat. Then we have the equality L minus lambda I applied to u is equal to L hat minus lambda I applied to v, which of course is equal to f on both sides, and the right hand side is equal to L minus lambda I applied to v, because on the domain of the operator L hat we have the L v equals to L hat v. Therefore, because lambda is regular for operator L, we can apply the resolvent and get that u is equal to v. So the result of application of a resolvent of L and the resolvent of L hat to arbitrary function of from L2 on the half line are equal. Therefore, the operators are equal. As the corollary, we get that the essential spectra of this operator L and L hat coincide. This is just the, for example, it is just the straightforward corollary from the Weil theorem of compact resolvent perturbation. We say that if two operators have compact resolvent difference, which in our case is trivial zero operator is of course a compact operator, then the essential spectra of this operator coincide. So this follows directly from Weil's theorem. And now we can try to match the essential spectrum of operator L hat with our set S. Therefore, the essential spectrum of operator L, the original operator, will also be S. We recall that our operator L hat is the prime sum of some operators acting on the finite segments of real line, and all these operators have purely discrete spectrum. We denote the jth eigenvalue of the operator L hat k as lambda jk. And we know that the essential spectrum of the prime sum of the operators is equal to the set of accumulation points of all the eigenvalues. Okay. So by direct calculations, we can show that lambda jk is equal to ak plus pi times j over dk squared, where dk is the difference between xk and xk minus 1. It is the length of the kth segment. Okay, no, well, this can be shown by just university methods, you know. And we split our sequence AK into two sequences: the negative part labeled BK and the non-negative part labeled as CK. I changed the numeration, so it is this both the sequences are numerated from 1 to infinity, or to up to some finite number if it is if there are only finite negative or non-negative elements of this sequence. We take also an assumption into account that the limit of decay is equal to 0. As far as I know, the case where the length of these intervals are separated from 0 is studied well. For example, I will show some references in the end. For example, Mark Malamud and his co-authors studied this case both on this problem and with next problem being the delta function potential and also for delta prime potentials, the prime sum of delta prime potentials. So we assume that decay tends to 0 as k tends to infinity, and we have the accumulation points of the non-negative part of this sequence. Of the accumulation points of the eigenvalues corresponding to the non-negative part of the sequence AK is only plus infinity, because this tends to this is positive, this tends to plus infinity. So the sum tends to plus infinity only. Therefore, the essential spectrum of the operator L hat is coincide with the set of accumulation points of the sequence corresponding to negative part of the sequence AK. I underline that this means that the essential spectrum of this operator depends only on the negative part of the potential and not on the positive. So the positive part can be arbitrarily chosen. As for the negative part, we will take some trick. We choose some sequence Sk such that our set S is the set of accumulation points of the sequence, and this sequence does not does not increase very fast. In fact, Sk is to be lesser than pi over dnk squared for all k, and also it should be all small of this sequence. So that as k times dnk squared tends to 0 as k tends to infinity. And we define bk is equal to minus pi over dnk squared plus sk, which is by construction is negative. And so this coincides with the previous definition. Then the sequence bk plus pj over dnk squared is, if we write down it explicitly, if j is equal to 1, it is just sk. And if j is greater than 2, this is some fraction for which we know that its numerator tends to pi squared j squared minus 1 as k tends to infinity, and it is just a finite number, and the denominator tends to 0. So this whole this whole set has only accumulation points being plus infinity. So the accumulation points of this sequence is the same as the accumulation points of the sequence Sk, which is S. And we know that the accumulation points of this sequence is exactly the essential spectrum of our operator. So we have constructed the potential being the potential of the form this form So the essential so that the essential spectrum of the operator L is exactly S. So the construction is done. Now we will try to apply the same method to the operator with delta potentials. So instead of characteristic functions of some interval, we have some delta interactions at the point xk. Again, this operator x in L2 on the half line, with the domain being W22 on the half line minus the sequence xk and a continuous function. And also boundary condition being Dirichlet or Neumann, I will consider Dirichlet only, but we'll show in some moment how the proof will change if Neumann condition will be applied. So I will not stop very much for declaring the correctness of the definition. If you are interested in this, you could read some papers by Savchuk and Shkalikov, operators with distribution potentials, or the works of the classical books by Toshio Kato, for example, where such operators are defined. I remember 4 different ways of defining such operators, from quadratic forms to some regularizations of the potential. In my work, in my work, I don't pay so much attention to the correctness of definition because under some conditions I will show later, this operator is well defined. It is self-adjoint. It is semi-bounded. For the correct definition of such operator, we have it to be semi-bounded. I will assume that is bounded from below. And if these conditions hold, then the operator given by such differential expression is well defined, is self-adjoint, is bounded from below, and is very good for our consideration. The problem is the same. Given a closed, now it is bounded from below as well, subset S of R. We will try to find values xk and ak parameters of the potential such that the essential spectrum of operator IH is equal to S. If we try to apply the same technique, that is to put the potential barriers at all points xk, the essential spectrum will always be empty because the prime factor of the exterior operator will be just minus second derivative, and the essential spectrum will be zero. Will be empty, not zero. Will be empty. So the next iteration of this method will be trying to apply the barriers, the impenetrable potential barriers at even points, not at all xk, but interleaving. So we split the sequence xk into 2 parts. Here, the yk is the subsequence with differences tend to 0, sk tends to infinity, and its sum equals to infinity because our points have to because our intervals have to be the whole half line in its union. Mk are some points lying on this interval, and we denote ak as mu k at the red points and nu k at the blue points. And we will tend nu k to plus infinity and get this way our auxiliary operator as spoiler. In this notation, our operators can be written as follows. And we note that this operator, in fact, is itself can be represented as the prime sum of some operators acting on the prime sum of L2 on IK. Its actions is written below, and its natural domain is W22 on IK minus MK and continuous functions with some Robin boundary conditions written as follows. This also can be shown. The correctness of this definition can also be shown by applying the results by Savchuk and Shkalikov in their paper or in some other methods. So let us construct the auxiliary operator. We will take nu k are equal to plus infinity for all k. So the auxiliary operator will be the prime sum of these operators with Dirichlet boundary conditions. It is easy to show that if we tend nu k minus 1 and nu k to plus infinity in these conditions, we can put this fraction on the left hand side, taking an inverse, and we see that this left side tends to 0. So indeed, if we tend nu k to plus infinity, we have the Dirichlet boundary conditions. And again, the spectra of all these operators, hk and hk hat, are purely discrete and can be found using direct calculations. But these values cannot be represented, as far as I know, as far as I tried to be said. I cannot put the exact, the explicit formulas for these eigenvalues only as the roots of some functions. To be put precisely, for the sake of convenience, we put mk being the middle point of this interval. I can also write down the answer for arbitrary mk, but they will be so difficult to show and to see and to analyze that it is not very useful. After all, we are here to construct some example of the potential with the prescribed essential spectrum and not define all the class of the operators of such way with this essential spectrum. So the proposition is the proposition which you can check by just applying some university knowledge that the essential the spectrum of operator hk hat consists of two sequences. The first one being 2 pi j over dk squared for all j from natural numbers, and the second part be some roots of the functional equation. The function fk hat will be defined on the next slide. And the spectrum of hk without hat is similar. It also contains the part of some functional equation, fk without hat, which we defined on the next slide, as well as some degenerate series. If nu k minus 1 is equal to nu k, then there is the second sequence in the spectrum being the root of the functional equation fk hat is equal to this value nu. This value nu. The function fk hat is the same as before. So the functions fk hat and f hat are presented here. They are very complicated to be said this way, but they are defined differently on the left and on the right half line. The function fk hat is just the cotangent or hyperbolic cotangent of some argument of some square root of lambda times square root of lambda. And the function fk without hat is defined more complicated, but in the denominator you can see the brackets corresponding to fk minus nu fk hat minus nu k minus 1 and nu fk hat minus nu k. So these degenerate sequences of eigenvalues are just the zeros of this characteristic determinant. This, in fact, is the characteristic determinant of this problem. If you write down the conditions given by these equations and the definition of the action of this operator, so the function must be continuous at point mk, and its derivative must have a step of the value mu k at the point mk. So you will have 4 equations, and this is the condition that means that determinant will be 0. So the non-trivial solution exists. And this, in fact, is the same, but for 2 conditions, because the Dirichlet conditions are much more simple to analyze. So these functions are continuous on each connected component of the domain, and strictly increasing on each of them from minus infinity to plus infinity. Therefore, the solutions to these equations are uniquely defined on each connected component. And we have some propositions showing that the auxiliary operator is just some kind of limit operator of some kind of limit procedure to the original operator. That is, if minimum of the constants of Rabin boundary conditions tends to plus infinity, then we have the convergence of corresponding eigenvalues of hk without hat to hk with hat. And we can show this analyzing the exact way of the exact form of this spectrum. First, we notice that the partial derivative of the function fk without hat or with respect to nu k minus 1 and nu k, this is the misprint. We show that these partial derivatives are negative, and therefore this function decreases on both arguments as nu k and nu k minus 1 tend to plus infinity. Therefore, the eigenvalues of this operator are increasing in both these arguments because they are the root of the function, and if function decreases, its roots goes right because of their monotonicity. So they are strictly increasing functions from minus infinity to plus infinity, and if with some limit procedure these functions go straight down, it's their roots are going straight right. So they are increasing in fact. So the function nu k minus 1 and nu k maps to jth eigenvalue of operator hk is increasing in both arguments, and therefore it is sufficient to consider only the case where they are equal, because we tend them to plus infinity, and we know that this function is increasing in both arguments, so we can consider only the diagonal. And in this case, the spectra of these operators can be ordered. The operator hk hat will be, the spectrum of it will be ordered as this, and the spectrum of the operator hk without hat is ordered as this. Here, the hat lambdas are the solutions of fk hat is equal to mu k. The lambdas without anything on top of it are the solutions of fk hat of fk without hat equals mu k. And lambdas with tilde on top are equal to fk hat are equal to nu k, which is equal to nu k minus 1. This is the second degenerate series of eigenvalues for this operator. So it remains to show that as nu k tends to infinity, we have the increasing convergence of the eigenvalues with odd numbers to the remaining hat ones, and the convergence of tilde eigenvalues to 2 pi j over dk squared. So this one tends to this one tends to this one tends to this, and etc. Okay, recall that the tilde eigenvalues are the solution of this function, of this equation, on the interval 2 pi j minus 1 over dk squared, 2 pi j over dk squared. And this function is increasing, strictly increasing on this interval. And if nu k tends to plus infinity, the solution tends to the right end of the interval, in which we have the left limit of this function being equal to plus infinity. So this proves the second statement immediately. To prove the first statement, we write down the function fk without hat restricted on the diagonal. Nu k minus 1 is equal to nu k. And in this case, it is very simple compared to this expression. It is very simple indeed. And we see that if nu k tends to plus infinity, this is just the function, linear function of a linear function, fractional linear function. So if nu k tends to plus infinity, we have the limit being minus 2 square root of lambda cosine over sine. And in this one, we have minus 2 square root of absolute value of lambda hyperbolic cosine over hyperbolic sine. So we have exactly the fk hat function. And we know that this convergence is decreasing. So the eigenvalues will increase for each respective j. And this completes the proof of this proposition. I'm sorry. Okay, so we have proven that we have some convergence of eigenvalues. And since decay tends to 0 as k tends to infinity, again, the accumulation points of the following sequence of the eigenvalues is just plus infinity, because this one has the only accumulation point being plus infinity, and this one all are greater than this value for j is equal to 1, because I remind you that this is written just the part of the spectrum of hk hat without the first eigenvalue. All this tends to infinity because of this tending to infinity. Decay tends to 0, this fraction tends to plus infinity, and all that are greater are also tend to plus infinity. So the essential spectrum of the operator h hat are again the accumulation points of the first eigenvalues of these operators. Okay, and we know exactly what to do now. We choose again the sequence sk such that S is equal to the set of accumulation points of this sequence and some conditions of its growth. They are growing no faster than pi over dk squared. And we define mu k being equal to fk hat of sk. Then mu k is negative by construction, by this condition. And the first eigenvalue is the solution of the equation fk hat of lambda is equal to mu k on the interval from negative infinity to 2 pi k over dk squared. On this interval, we know that there are only one solution to this equation, and we know the one solution which being sk. So this is the first eigenvalue of the hat operator. So the essential spectrum of h hat is the set of accumulation points of lambda 1 k hat, which will be sk. So it is equal to s. Thus we solve the problem for auxiliary operator. It remains to show that the resolving difference is compact between these operators, and then we will finish our construction. Okay. It remains to find the values nu k such the essential spectrum of h and h hat coincide. We will show it in the way that the resolving difference for values nu k large enough will be compact, and therefore the essential spectrum preserved. Okay. We recall that for the correct definition of both operators, I speak some words about the correctness of definition. We know that the operator h hat is by construction bounded from below by minimum of s, and we have to make sure that the operator h will also be bounded from below by some constant. By definition, by construction, it can be shown. In fact, there exists some sequence nu k naught, such that for every sequence being larger than this sequence for all coordinates, the operator h is bounded from below by minimum s minus 1. Instead of minus 1, we can write down minus c for every constant c. The sequence depends on this constant, of course, but for every sequence, it exists. If you try to tend this constant to zero, then the sequence tends to plus infinity. And the sequence, in fact, is determined by the condition being lambda 1 k without hat being greater than lambda 1 k with hat minus 1. So we have the convergence of this of lambda 1 k to lambda 1 k hat. We proved it. on the previous slide, on some previous slides. Yeah. And using the epsilon delta definition of the limit, you can for epsilon equal to 1, we can show the the value nu k such that nu k naught such that for every nu k being greater than nu k naught, we have this inequality. And this inequality, lambda 1k with hat, are measured by minimum s, and this one is just the minimum of the spectrum of the operator h. So the operator h is measured by this constant. So we have, for the correct definition, for the correct definition, we must have nu k being greater than this sequence. The problem is that this sequence is defined in such way it can't be write down explicitly at all. So we know that this sequence exists, but what is their asymptotics? How fast they grow? Can we write down some estimates on this sequence, not using itself? I don't know how to come to this problem, how to come to the solution of this problem. So this is only the non-constructive point in the whole construction. So I wrote in the abstract that my proof will be constructive. So this is the only moment that is not constructive. All the previous where you can solve the functional equations, you can make a program on the computer that solves it numerically. So this is a very constructive point. This one, no. This one is not constructive at all. So this is the only problem in all this talk. Okay. For the sake of convenience, we choose decay being of the special form, being equal to pi over k square root of mk, where the Gauss sequence mk satisfies the following conditions, which are in fact very understandable. So mk being positive, of course, mk increases, of course. This needs for us for decay to tend to 0 as k tends to infinity. Okay, mk being O small of k to the power of epsilon for all epsilon greater than 0. For example, mk can be equal to the logarithm of 1 plus k. This one is used in some technical results which are not presented in this presentation. And the third condition is that there are some points of set S on this half line from negative infinity to M1. So it's just the matter of the first term of the sequence. It's just a matter of this. And the conditions on Sk now look like this. S is equal to accumulation points, and Sk are lesser than Mk times k squared. If we put k is equal to 1, we will have S1 is lesser than M1. So the third condition shows us that this actually holds. So this can be satisfied. Yeah. And we are ready to write down some result with difference. Before I start this final part of my talk, I tell that this part is much better and in much general way is proved in the paper by Jussi Bent and Andrei Hrabusovsky, which Jussi shared with me before this seminar. I proved this the following propositions and theorems in case decay is equal to this one, and he proved it in much better way for arbitrary decay tending to 0. So in these terms, his proof is better, but I write down some elements of my results as well. So let f and j being from L2 on the half line, we denote u being r lambda of h applied to f being from the domain of operator h. V is r lambda of h hat being from the domain of h hat. And by direct calculation, one can show that the quadratic form of the resolving difference can be written in the following way. It is just the some usage of the integration by parts formula and using some the exact forms of these operators. So I didn't put the technical details here. But you can say why I put this term, because u of 0 is equal to 0 because u lies in the domain. I write down this extra term to show that in this term also there are also v prime of 0 plus, and if we had Neumann conditions instead of Dirichlet, this term will also be 0. So this doesn't make any difference in the proof. If we put the Neumann conditions instead of Dirichlet, there will be no difference in our proof. Okay, so we define some constant ck, which is equal to mk minus 1 to the power of 3 over 4 times k plus 2 to the power of 3 over 2, and we define some operators. You see, in this sum we have something like the scalar product in L2 small. So we will make the usage of this fact. We define some operators being just the u in the points of yk and v prime in the step of v prime in the points uk. So this one and this one, but with some coefficients ck, which are used in the proof. So in this way, the resolving difference, the quadratic form of the resolving difference is just the scalar product of the results of these operators. And if we put down, if we take this operator r hat to the left side, of course there must be star. So this must be not r hat, but r hat star, the adjoint operator, of course. So the resolving difference is equal to the composition of two operators, r and r hat adjoint, and the proposition will be, for let epsilon being arbitrary positive and fixed, and nu k being greater than some value depending on ck. Then the operator r is compact, the operator r hat is bounded, and therefore the resolving difference is compact. So we proved that. So if we prove this statement, we will have that the resolving difference being compact for nu k large enough, and therefore the essential spectrum holds. The essential spectrum remains equal to the essential spectrum of the auxiliary problem. Okay, so again, this statement is much better proven in the works of Jussi and Andrei, and some technical estimate. It's just the technical proof as well is my proof and their proof. They are the same in the terms of techniques, but they are working with much better generality. To prove the compactness of the operator, we can approximate it with the finite dimensional operators, which is just the cutoff operator. And the norm of difference will be as follows. And we can also see that these operators form the fundamental sequence. So the difference in this estimate will be this term minus the same one according to m. If we write down rm minus rn, we will have this term minus the same with the letter m. In the supremum will be from n to m. The rest will be the same. Here kappa is some constant depending on the set S. And the estimate of the norm of the operator R hat is, in my proof, it is obtained in some very hard to understand, very hard to put on the slide proof. so I didn't try to combine all these results into some horrifying estimate. So I think I'm done here. If you have any questions, please ask me whatever you want. Thank you. So the references, of course. The first one, and plus some classical books like Toshio Kato, are here to for you to read about the correct ways of definition of the differential operators with some non-usual potentials such that delta, delta prime, and etc. The first one is the best after of all. The third and fourth papers deal with the same problem, but in different aspects. So the third one deals with operators with delta prime potentials, and the fourth one deals with delta potentials, but is concerned with some criteria of the discreteness of spectrum and some results on the stability of essential spectrum, but not the inverse problems. And the final two papers were shared to me by UC Band. Actually, they contain some results on this problem on some finite line segment, and also they can restore some discrete spectrum, some finite part of the discrete spectrum. So they have much better results than mine, but they are working in well, their proofs are some different, but if you want, you can read down their papers as well. There are much of the same results. So thank you.